CTO of Rotational Labs. Take it away.
Hello. Everybody hear me okay? All right. All right, in a galaxy. Just kidding. These were probably the metrics that many of us grew up using, doing kind of traditional machine learning, which now feels like the old kind of machine learning, right? And for me, at least, these kinds of metrics provided a very pleasant sense of kind of stability and certainty when we were doing kind of the old version of machine learning. So if your F1 score went up, you knew that things were getting better. If your mean squared error went down, you knew you were getting closer to what you wanted to be. So there was kind of that sense of confidence that these metrics gave you a way to navigate what you were doing when you were doing machine learning. But something strange has been happening for me the last year or two, and potentially for many of you, which is that a lot of these metrics have sort of receded from my daily workflow, which is very disorienting because I depended a lot on those. So that's kind of what this talk is all about. It's sort of, where have all the metrics gone? Where did they go? What happened? And sort of for context, if you're new to the PyData community, I've been doing this a long time. About 10 years ago, I wrote a Python library called scikit Yellowbrick, which some of you may know about, maybe the old school people out there. Yellowbrick is an integration of the scikit-learn and matplotlib APIs. And so the intuition is that if you can visualize in plots kind of how things are going, that gives you a signal about whether or not you're on the right track or if you've gone off course, and maybe gives you even some hints about what you should change in order to kind of get back on track. So that was sort of the core idea behind Yellowbrick. So when I was teaching machine learning at Georgetown, these were some of the Yellowbrick visualizations that I would teach my students to kind of use to help them steer their model selection and feature engineering and hyperparameter tuning. So in the case of, let's say, a regression model, you've got the residuals plot, which kind of shows that like cone-like shape that tells you that you are experiencing heteroscedasticity. And then on the other side, for classification models, the confusion matrix allows you to zoom in on exactly which categories the model is failing to correctly label, and like how often it's labeling at that, and also like what does it pick instead of the right answer. So it gives you a lot of information about kind of what's going on. So in each of these cases, the visualization kind of illuminates a very specific kind of error, a kind of wrongness that gives you a map to how to get to a better solution. So it's no wonder that that kind of gives a sense of control and comfort in what is kind of a non-deterministic world that we all live in. And they make the wrongness feel discrete, right? Like it's like, okay, if I can just figure out what's going on here, I can get it better. Unfortunately, these tools have not traveled very well to this brave new world that we're doing with generative AI. And I think my hypothesis is that the core problem is that in the generative AI era, wrongness is no longer one-dimensional. Because generative models can be wrong in a lot of different ways all at once, right? They can be wrong semantically, which I'm sure all of you have experienced. They can be wrong sort of stylistically. The tone can be bad and stupid. They can be wrong structurally, right? So they can give you back something that's not an informed consent form, right? Something that's some other structure, not a valid output that you were looking for. They can be behaviorally wrong, like they can do things they're not supposed to do, like delete your database. So they can do a lot of things wrong all at the same time. And traditional metrics kind of assume that error exists on a single axis, right? Like it can be quantified as sort of a scalar difference between what you actually got and what you actually should have gotten and what your model predicted. So to understand what has really changed, I think it helps to kind of go back in time and think a little bit about the workflow that we were all using just a couple of years ago that exploited this sort of very simplistic notion of wrongness. So I think that probably most people, maybe if you haven't seen this exact chart, like you can kind of see your old process here in this visualization, right? You would get a juicy big new batch of data, and then you would do the workflow, right? The data science workflow. You would do exploratory data analysis. You would do model selection and comparison. You would tune those hyperparameters, and then it's an optimization problem, right? You just keep going until the metrics go up or go down, depending on what you're trying to do. And then, once you're done, what do? You pickle it. You pickle it and you throw the pickle over the wall, and then you just wait for a new batch of data and you start all over again, right? So that was like the workflow that we all used. And on our side of the wall, error was numeric. Error was easily quantifiable, but I think what has happened is that now we live on the other side of the wall. Applications land. And on this side of the wall, error is higher dimensional, and it's not as well defined, it's not as concrete. And I think a lot of us live on this side now. I mean, some of us are probably still doing traditional machine learning occasionally, hopefully, because it's still good for stuff. It's just that, all of us are kind of now trying to figure out how to navigate this new space where most of us are not training foundation models. We're using them. So that's why we live on this side of the wall. And once you kind of start being a user of models rather than a maker of models, the feedback you get when things go poorly isn't a number. It's sort of unclear, like, oh, it hallucinated, or this isn't good, or I don't like this, it's inconsistent, this is too vague, this isn't right. Like, that's the feedback you're getting. It's not a scalar anymore. And, it's sort of multidimensional. And in a lot of cases, accuracy actually isn't well defined anymore, even though I think a lot of us still are using this word accuracy. But like, when you use that word, do you actually mean like mathematical accuracy, or do you just mean like alignment, right? Like, it feels right, the output is better, right? So I'm not even sure if accuracy is that well defined on this side of the wall for most of us. Well, I would love to tell you that I have invented a new plotting library that tells you how to kind of extend all of those metrics to this new kind of multidimensional era of wrongness. But sadly, I cannot tell you that. To be honest with you, I'm still kind of figuring this out too. And that's what this talk is about, me sort of, I guess, decaching what I've thought about, what I've figured out so far. I think that the key, though, is coming up with a better shared vocabulary for describing what specifically can go wrong in LLM outputs. And so what I would like to do is walk you through some of the different error modes, failure modes, that I have been noticing. Some of these are names, like words that already exist out there, and so if you Google them, you will find like archive papers about them. Others of these, I just sort of had to make up a term to talk about what I was noticing, and so just full disclosure. But I'm going to start with one that's particularly close to my heart, and that is domain failure. So for a long time, my focus was in small language models and building domain-specific models using kind of computational linguistics, old technology. But the idea was to try to figure out how to build models that were very relevant to a specific domain. So domain failure is when the model sounds authoritative, but it gets details wrong in ways that only a true domain expert would be able to identify. So I have found that LLMs frequently drift into this kind of subtle wrongness. So what happens is that the output sounds right if you're a layperson, which, to be honest, most of us are lay people in all of the things that we do, except for those maybe 2 or 3 things in which we are domain experts, right? So we are all lay people in most things. And so when we see the outputs, they use the right jargon, the structure seems right, it looks great. We didn't have to write it from scratch. It's kind of impressive. But without that domain knowledge, which, is oftentimes, it's kind of experiential, it's embodied knowledge. So it's not really fair to expect an algorithm to know kind of embodied knowledge. Without that domain knowledge, things kind of can go wrong. And so I wanted to tell a little story. Over the summer, my teen was going to go to the Tyler, the Creator concert. Tyler was touring in our neck of the woods. And it was very important all of a sudden for us to make a custom suit. And so anybody sew, home sewers out there? One more than, okay, cool, thank goodness. There's 3 of us in this room. I've been a home sewer most of my life. I still have the same sewing machine I had at 13 years old, which is a long time ago now. But I've managed to hang on to it and maintain it. And so I agreed to make this suit. And then as I was getting close to the end, I realized that it had been kind of a while since I'd had to install a zipper. So if you've sewn before, zippers are sort of in the category of they're pretty hard. I think that it's sort of poorly understood that sewing is like an engineering task, right? Because you're taking these 2-dimensional things and creating 3-dimensional structures out of them. So it's fundamentally complex engineering task. So it's quite difficult. But be that as it may, I asked ChatGPT for help. And the reality is that it confidently sort of tried to help me deconstruct the zipper installation step, and it sounded very authoritative. But in the end, I had to do a lot of seam ripping because it was all wrong. Everything it said was wrong, and in the end, I had to rely on my own expertise and my own memory of how to kind of flip things around and align the different pieces. And I think that this is an especially dangerous type of failure because it's the kind where the only defense against this is expertise, right? This isn't something you can solve by having another AI evaluate ChatGPT's answer, right? You have to have a real human seamstress look at this and be no, right? But otherwise you can't know. So that's kind of tricky. This one is a little bit less tricky. So form failure is another dimension of wrongness that you can see in LLMs. So form failure happens when the model produces output that's in the wrong structure, even if the content is otherwise fine. Now, this kind of failure is bad because it breaks downstream systems, right? If this is in JSON, it's not getting ETL'd into the database, right? So it is kind of a problem because even if all of the input data is right, the syntax has to be right too. The good news is that with these kinds of failures, like structural failures, form failures, is there actually are an increasingly amazing number of open source tools out there that you can use to help you solve these kinds of problems. So you can use something like PyData to define a schema. which fields are expected, the types, the nesting, et cetera. And then you can use something like outlines that actually provide that schema to the model at inference time, which constrains the generation that comes back to make sure that it respects that structure. But, so even if the content and the structure are right, there are even other ways that things can go wrong. So here's a third kind of failure that some people maybe will recognize. This is mode collapse. Sometimes people call it model collapse. But mode collapse is when a generative model stops producing variation, even when the task calls for diversity. And some of you may have encountered this term before in the context of generative adversarial networks. Anybody a GAN person out there? Okay, I see a couple of you. So in GANs, you can sort of see in this MNIST generation exercise here, this is mode collapse in a GAN. So that top row, that's kind of the GAN working correctly. So it's doing kind of pseudo handwriting generation. And in that top row, you can see that it's generating digits, between 0 and 9, which are the MNIST digits. But in the bottom row, it's sort of degenerated into this sort of repeated symbol that's happening over and over that's kind of like not a 6 and also not a 6. It's sort of kind of a pseudo number, and it's just repeating it over and over. That's mode collapse. So I think that you can see a similar phenomenon in language models, especially if you have experimented with synthetic data creation. So I was talking to somebody about synthetic data creation before my talk. And actually, I think that this is, mode collapse aside, generative AI is a fairly good solution for the problem of we don't have data, we need to create synthetic data, or the data that we would use has PII in it, so we can't use that. So synthetic data, I think, is a perfectly valid use case. It's just that then you have to think about this dimension of wrongness, and you have to figure out how to adapt a little bit. So in this example, I asked, give me 5 alternates to the quick brown fox jumps over the lazy dog. And it says, the speedy brown fox leaps over the tired dog. The nimble brown fox bounds past the sleepy dog. The lively brown fox vaults over the sluggish dog, right? So technically, it's given me 5 alternates, but the variance is very poor, right? So like all of the examples include the same animals, and they all include the same colors. There's no grammatical variance, right? So like if you're doing synthetic data generation, I think that this is a valid problem. LLMs do, tend to collapse into high probability phrasings and structures, and that's going to be true no matter what kind of data you're trying to generate. So consistency failure is yet another type of failure. This is one of those where I think I've been calling it consistency failure. If anybody knows another term for this, then let me know. But basically, I think of this as where the model gives different answers depending on which day you ask it the question, or maybe like slightly different phrasings of what amounts to essentially an identical prompt. And now this is very unsettling if you've ever noticed this before, because it really breaks our assumptions about how software should work, namely that it be mostly deterministic. And even if we assume that AI is kind of like inherently a little bit stochastic, I still expect, like, if you say you can do a thing today and I ask you the same question tomorrow, like, you should give me the same answer about your capabilities tomorrow. So here's a simple case. This is early in the year. So this is probably like February, March. So many iterations of Gemini ago. But so this is like pre-Nano Banana. But I asked Gemini if one day I asked if it could access a YouTube link, a public video, and summarize it for me. And it said, yes, sure. And I thought, well, of course you can because you own all that data, Google. Like that makes sense to me. It seemed intuitive, right? And it also thought it was intuitive that it should be able to do that. And then I asked it the same question the next day, and it gave me this sort of baffling apology. This kind of instability is bad kind of for another reason, which is that it erodes people's trust. And if you're trying to get a bunch of skeptics to buy into AI, like this is not what you want to happen when you're doing your demo, right? Like the thing that worked yesterday, now you're showing it to these skeptics in your organization and all of a sudden it's like, no, I can't do that, right? That's kind of embarrassing. So, you know, it's something that, you have to kind of figure out how to navigate. This is almost kind of like the mirror image of consistency failure, which I've been calling boundary failure, another term that potentially I just made up. But basically, I'm thinking about boundary failure as like the model crosses some line and it does some task that it should not do. And this is very common. And basically, you know, the model is doing things that it's not supposed to do in the first place. So this example is somebody hacked the chatbot for a car dealership, and the chatbot's ostensible purpose was to answer questions about car financing and inventory, but this chucklehead asked it to write a Python script, yay Python, ask it to write a Python script to solve the Navier-Stokes fluid flow equations, which it did. So now what we have is a car dealership chatbot that is behaving more like a computational physics assistant. So, I mean, this is kind of a funny example, but hopefully this sort of clues you into, you know, some situations where like boundary crossing could create like serious governance and safety concerns for a project. This makes you kind of realize all of a sudden like, oh no, I need to actually like gate the behavior. And then I want to talk about one more type of failure in depth, which I call temporal failure. And that's when the model fails to account for the passage of time. So if you've used any AI coding assistant, which I will admit, I have been sort of slow to adopt these AI coding systems, partly because I'm old school, and it's partly because of things like this that really irritate me. Like when you've been part of the open source software community, like you realize that things are always changing, right? Like the API is always changing. There are new versions that are coming out all the time. Functions are getting deprecated. But you know, AI coding assistants don't understand that. They don't understand the passage of time. And so they'll suggest APIs that have been deprecated in functions whose signatures have changed. This kind of top example is from the like cursor message board of somebody saying, you know, it keeps proposing these outdated API calls that I have to fix then. And the reason that this happens is because LLMs are temporally blind, and that I did not invent. That's actually from this paper about temporal blindness in LLMs. And in this paper, the researchers have like observed this phenomenon and measured it, which is basically that LLMs like have difficulty incorporating elapsed time, which has a lot of implications if you're a user and you're interacting with an agent that's like a long-running agent, or that needs to take into account, you know, what tomorrow means or last week means or things like that. Okay, so we've seen a few different dimensions of wrongness. I think there are many, many more. Here are some. Again, some of these I made these up, or made up these terms to help explain things that I was noticing, which means like you can make up terms too, right? I'm giving you permission. In fact, I encourage you to make up terms and kind of use them to communicate with each other, because I think it's a lot more productive to start zooming in on these specific types of failure than to say things like hallucination, which kind of doesn't really help you know what to change, right? But each of these kind of illustrates why generative AI can't be evaluated using a single metric like accuracy. So what I'd like to do next is talk about how we might try to measure these in a structured, meaningful way. So step one. Up to this point, we've looked at ways that LLMs can fail even when things seem like they're going right. But part of the issue is that if we assume from the beginning that the agent works, we're going to overlook the places where it does not. And we also will have no instruments to detect those failures. So the paradox here is that the most reliable way to build robust agents is to start from the premise that they aren't reliable yet. And that's a little bit counterintuitive. And it requires a little bit of humility. So that's maybe also a problem for some people, but hopefully none of us in this room. Okay, so look at these two versions of kind of the beginning of a sentence, because they look almost identical, but I think they produce very different engineering cultures. So the first one, we are building an agent that it carries an implicit assumption that the capability already exists. And your job is simply to implement it in Python or LangChain or whatever. So that mindset skips past uncertainty, and it skips past experimentation, and it sort of blinds us to the multidimensional wrongness that we explored in the last section and that you are sure to encounter when you actually try to build this agent. But if you say, we want to test if an agent can, we are not assuming anything. We're framing the project as an experiment that has measurable hypotheses and observable failure modes. And it gives us permission, actually it kind of obligates us to define what success would look like or what failure could look like and how we would measure those outcomes. So different projects are vulnerable to different dimensions of wrongness. And if you try to measure everything, you're going to get overwhelmed. So my advice is to pick 2 or 3 or 4 that are the most relevant failure modes to your problem and that make evaluation tractable and meaningful. So these are some suggestions that are sort of based on the failure modes that I talked about in the first part of this talk. But again, borrow from mine, make up your own, kind of make your own checklist, and then at the onset of each project, go through and pick 2 or 3 or 4 that are relevant for your project and that match kind of the stakes that you're working in. So for example, if you're building a system that outputs JSON, structural correctness is probably a make or break situation, and so you want to kind of make sure that form failure is at the top of your list. If you're building like a research assistant, then hallucinated citations are way worse than being too verbose, right? Because most academics are too verbose anyway. But hallucinating citations can get you fired. If you're deploying in like a regulated domain like healthcare, like the last speaker was talking about, then boundary failures, where the agent does something that it's not supposed to do, that's probably going to be top of your list. Or maybe, kind of avoiding PII leaks, that might eclipse everything else. So once you've identified the failure modes that matter most, the next question is, how do we design experiments in a way that let us isolate and measure this kind of failure? So this isn't the answer, just as a TLDR. But as a starting point, I call this the mega prompt. Has anybody kind of seen something similar like this at work or had somebody try the mega prompt? Okay, I see some of you. Right, so the mega prompt consists of one model and one massive prompt. And now that we are allowed to have 100,000 token context windows, it feels like maybe we should be able to shove it all into one, one agent to solve the entire problem. This is attractive. I think especially because it appears to sort of collapse complexity, and everybody, is always trying to avoid complexity, which is funny because reality is complex. So if you're avoiding complexity, what are you actually avoiding? But instead of building a pipeline, you effectively are just writing a paragraph of text, right? That's what machine learning is now. It's just writing sentences. But unfortunately, the mega prompt collapses under the failure modes because it doesn't give you any visibility into where the failure came from. So if your mega prompt makes a bad generation, what is the root cause? Did the model misunderstand the task? Did it ignore some constraint? Did two instructions contradict each other? Did it suffer mode collapse? The failure surface area is massive. And it's so big that you can't isolate the problem. So to measure wrongness and hopefully reduce wrongness, we need a better approach. When we decompose a problem into tasks, and I actually have been noticing this notion of task decomposition is coming up in a lot of the talks and the tutorials yesterday, which I think is a very good sign. We're on the right track. When we decompose, we turn that black box into a sequence of testable, observable steps. So instead of asking one model to do everything all at once, we break down the workflow into discrete tasks. Each task has a clear purpose, a bounded input, a kind of clear expectation for the output. And if you have built ETL pipelines, distributed systems, production machine learning workflows, this will look somewhat familiar to you, right? Because this is how you build systems. You break things down because then the failures are much easier to isolate. And decomposition also makes rigorous evaluation much more realistic and possible. So when you have clear task boundaries, now you can evaluate each step on its own terms. And each component can kind of have its own failure modes, right? So was the wrongness introduced during the retrieval step, during the fact-checking step? Where did things go wrong? And instead of one giant blob of wrongness, we have a map. And it tells us where the wrongness is entering the system. So now that we have decomposed the workflow, the next question is how do we actually measure wrongness inside each one of these tasks? So in this next section, I want to shift from talking about anticipating wrongness to measuring wrongness. So we've been talking about why traditional metrics don't work and why LLM failures are multidimensional and why decomposition helps us with visibility. But now we want to kind of give ourselves some instruments around that visibility so that we can capture wrongness in ways that are measurable and repeatable and that we can communicate to our team. So this is about building a measurement strategy. And I think that is a little bit of a mindset shift if you're used to kind of having default F1 score, area under curve, precision recall curves. If you're ready to, you used to having those metrics ready at hand. This is a little bit different because it means you have to do a little bit more work. You have to come up with a measurement strategy that's going to reflect the kinds of wrongness that are most relevant to your project. So we're not just measuring, we're not just chasing accuracy, we're actually going to characterize behavior. So there are a lot of different approaches, but basically evaluation kind of boils down to good compared to what. And whether you're doing kind of like standalone evaluation of documents or kind of comparative strategies, what you want to do is try to move away from vague, undefined absolutes into more measurable dimensions. So let's walk through a case study to kind of make this a little bit more concrete. So imagine that our friend Helen, who is a consultant, and every day or every week at work, she has to spend like hours going through like Slack threads and Jira tickets and emails and conversations that people have had to compile these client briefings for her company's customers. And it's really boring and repetitive, and probably the customers aren't even reading it anyway, and so it's kind of demoralizing. And so she decides to create an agent, Otley, and Otley is going to build these client briefings for her. And because it's agentic, it can kind of do some of this work, right? So if she gives it a code name for a project, it can go and hunt through Jira and Slack and all those things, kind of compile the report, and synthesize everything and return an HTML report that can be rendered directly in the client portal, right? So trying to remove all of those manual steps that Helen hates. So what should Helen do first before she gets started? Plan to fail. She should plan to fail, right? So what could go wrong? So remember, she needs to kind of think about what to focus on when she's doing her evaluation. So is the output valid HTML? It seems like that's pretty important, right? Because if it's not HTML, it's not going to get rendered in the client portal, and then she's maybe going to be in trouble. So that's going to be one. Let's say consistency is important, right? Like we don't want it to work sometimes and not work other times. And maybe we also want to make sure that this stands up to domain experts, right? It doesn't collapse under domain expert scrutiny. So let's see how she can evaluate each of these in a concrete way. So let's talk about the first one, rendering HTML. Here, evaluation is really actually kind of simple, right? Is the output valid HTML or not? It's a binary, machine checkable criteria. We actually don't need a human to do this. We can just have like a validator. And if we want to eliminate this kind of error altogether, we know that we can use tools like PyData or outlines to enforce structure at generation time, which is kind of the ideal case, right? Because that means the metric is obvious and evaluation is cheap, and the feedback loop is straightforward. Unfortunately, it's not always going to be quite this easy, and a lot of times it is going to require human judgment, right? So if domain expertise is required, the only defense is domain experts. So how are we going to do that? So for this failure mode of collapsing under expert scrutiny, I would suggest maybe creating something like a Likert scale for this one, right? So then Helen can send out Otley's briefings to people who are in her company who are in the know, and they don't have to write a detailed feedback report. They can just kind of give her a number between 1 and 5, instead of saying, this seems off or this seems bad. So she gets kind of these quantifiable signals, like 1 means that it's completely incorrect, 5 means ship it, and 3 is somewhere in the middle. These become sort of measurable outcomes that she can track over time. And that's how subjective judgments start to become data, right? So let's talk about the consistency one. So for consistency failure, where the model has different behavior over successive runs with the identical prompt, she could actually do an experiment where she can generate a lot of outputs potentially across time. And then she can define a function. So if we let G be the n generations, from that same prompt, we can define a similarity function. And this could be like cosine similarity or embedding similarity, whatever makes sense in the context of the content, that returns a score from 0 to 1. Then we can compute the average pairwise similarity across all of those generations. And that gives us a simple interpretable metric of how stable the agent is. It's not accuracy. Maybe it's something like output consistency, which is just a metric that you will have just made up. But it comes with math, right? It's rigorous, it's repeatable, it's explainable. We're translating kind of a qualitative impression, like this seems inconsistent, into a numeric measure that the team can track over time. You don't need to be a statistician to design this metric. This isn't this isn't a dig at Alan, but like you don't have to be a math professor to invent this kind of stuff, right? You're allowed to do this too. You just need to understand what you want to observe and how you want to measure it. So what is the big picture here? I think the big picture is that you get better agents if you measure wrongness with intention. Traditional machine learning metrics gave us certainty, but generative systems require kind of more nuanced solutions for measurement, and wrongness is going to be multidimensional. So it means your evaluations probably need to be multidimensional also. And so it's going to probably look like a mix of binary checks and maybe some automated checks with things like PyTest, maybe human ratings with Likert scores, and some kind of lightweight computational metrics. And that's kind of just the new standard. And that's how you build systems that you can trust. But I also want to say that the open source ecosystem is really rich here, so you don't need to like buy some fancy proprietary tool to get started here. You know, a lot of the tools in this ecosystem actually predate the LLM boom. And so you know they're super reliable. They've been around for years and years. You know, things like PyTest, which you can use things like parameterize in PyTest, you know, to make sure that you're doing kind of evaluation of prompts and outputs. And then you can combine in newer tools like Outlines and Pydantic and Langsmith and DSPy and, you know, all of those things to give you that structure and the logging and like evaluation harnesses and guardrails and stuff like that. These are kind of quickly becoming the stack for AI evaluation. So thank you so much. I hope this gives you a new vocabulary, but more so like a new confidence for evaluating in the generative era. So thanks so much.